Chapter 2 is all about functions, and every function we look at is really either a parent function or some transformation of a parent function. A parent function in general is a very simple form of function that depicts most or all of the type of the function's behavior. So for instance here, I have the parent function I've graphed here, the parent function of a linear function. So this one is just x, y equals x. That's what you can see in this first one here. And you see how its behavior is naturally it's just a increasing slope. It has a y-intercept right there. And every other line is really just a transformation of this line here. And I'll talk about transformations in a second. Another type of parent function is the absolute value function. That's where you have the absolute value of x. So this is a parent function. It's just kind of two lines that meet at a point right there. Okay, the next one we have is x squared. This is a quadratic function. It's a parabola shaped function. And this is a very common graph to use in mathematics. It's very, very useful in a lot of weird ways. Also, x to the power of 4 is very similar. You can see that it's a little bit shallower. The green is x squared. The purple is x to the 4th. It's flatter more at that minimum point right there, and it goes up higher sooner. The same thing with x to the 6th. Even flatter, and it goes up even faster. But you see they always meet out at 1, 1. That's because 1 squared is 1, 1 to the 4th is 1, 1 to the 6th is 1, and so on and so forth. And so all of these you can keep plugging more and more of these powers that are even, and you always have these flatter. It's going to get closer and closer to like just being a box shape, but it'll of course never get to that because it's always a smooth curve. Okay. Let's get rid of those and talk about x to the power of 3. This is a parent function of the cubic or odd powers of polynomials. And you see how it kind of does like a flat line here and then it increases. It's only flat for a moment. This is actually called a saddle point. That's where it goes from increasing to kind of flatlining and then it increases again. Another saddle point where it's decreasing, it flatlines and decreases again. But of course, x to the power of 5, very similar. X to the power of 7, very similar. It gets to more and more, flatter here. And of course, they meet at 1, 1. 1 cubed is 1. 1 to the 5th power is 1. 1 to the 7th. And then negative 1 cubed is negative 1. Negative 5, negative 1 to the 5th power is negative 5, and so on and so forth. Okay, so that's the cubic and odd power polynomial parent functions. Okay. Let's look at the next one, which is the square root function. Square root of x. This one's a little bit weird. If we take x squared, you'll see that this portion, the green portion right here, is very similar to this portion. It's actually only reflected. We're just ignoring this part. And we're only considering this portion and this portion here. They're actually called inverses of each other, which I'll talk about in the coming video. But this is the square root function. It is not defined for anything negative underneath the square root. That's because the square root of negative numbers is a complex number. And here we are graphing on the real number plane. So complex numbers cannot be graphed on this plane. Okay, and that's the square root function. All right. And we can also have things like cube roots. You see here, we do have everything. That's because the cube root of, for instance, negative 8 is negative 2. It is not complex, so we have the entirety of it. It's actually quite similar to the square root, but you see it's much kind of a flatter line there. but the square root does not have the negative portion. The cube root does. So that's a very big difference there. And of course, it's red, I think. Yeah. You can see that the red line is close. It's actually just a reflection across a certain line, and that gives you the blue line. That's because there's what are called inverses of each other. Now, some more parent functions that we are not talking about yet are exponential functions. This is like 2 to the power of x. It goes like that. Also, log of x. The purple here is log of x. If I took log base 2 of x, then you see that these two functions are actually inverses of each other. Again, you'll learn about that. But these functions we're not talking about yet. That's a later video. And then, of course, some more functions that we will not talk about in this class is trig functions, which are sine. We'll do cosine. And you get some interesting ones like tangent. Then you have cosecant, cotangent, and secant. But those are trig functions, and we won't be talking about them in this class. Okay, now let's talk about transformations of functions. A transformation looks like this. It's where you have your function and you have a times the function and then b times x minus c plus d. These are all a, b, c, and d are all transformations on our function. So for instance, let's say our function here is x squared. So this is the parent function of x squared. That's where a is 1, b is 1, c is 0, and d is 0. That means we have 1 times x, which is x, minus 0, 0. So we have x squared on the inside, times 1, which is just x squared, plus 0, which is just x squared. So this whole thing collapses down to y equals x squared. Now, let's look at c and d first. If c is positive, you see that it moves to the right. That's all that changes there. Of course, c being positive will end up looking like a negative c in the actual function. So for instance, let me get it on 3 here, if I can. 2, okay. If c is 2, then really this whole thing collapses down to y equals x minus 2 squared, that quantity squared. You can write it like this. Y equals x minus 2 squared. And you see they're the exact same thing. If I move c just a little bit, you'll see that it just moves slightly. That's because it collapses down to this thing. Y is 1, b is 1, d is 0. Yeah. Okay. So if c is positive, then it just shifts it to the right. Let me go back to the home screen here. Just a little bit. If c is negative, it just shifts it to the left. And if c is 0, we get right back to our center. D is similar. If d is positive, it shifts it up. If d is negative, it shifts it down. Okay, now a and b are the more interesting ones because they're multiplying. If a is greater than 1, this one makes it skinnier, but what it really does is it's stretching it vertically, because all of these values are being pulled upwards. Imagine putting your hand like right here and putting your hand like on this function like up here and then pulling them apart, and you end up stretching this more and more vertically. You're just pulling it out. If a is less than 1, you're compressing it, you're flattening it out, and it flattens all the way out until you hit 0, and where it's completely flat, It's just this vertical line here. Then if you go negative, now you have a flipped version. It's just really flipped of the positive version. So if a is -1, this is the exact same thing flipped as the original graph. It's just flipped there. That's all the negative does. It just flips it. The properties, however, are the same. If you have less than -1, you're stretching it out vertically. If you have it between 0 and -1, you have a flattening of it. So that's what the A does on the outside. It's a stretch and a shrink, or a stretch and a compress, you can think of it as. B is similar. However, if B is positive, or no, that's the same thing. It's the same thing, but it's in a different kind of way. What you're going to end up seeing is that if B is positive, B is on the inside of the function, and this is equivalently like we're dealing with the horizontal. On the outside of the function, some multiple or some addition like A and D are on the outside of the function, B and C on the inside. What you're dealing with here is the vertical portions of the graph. So A in this case stretched it vertically and flattened it vertically, flipped it vertically, all those types of things. D here shifts it vertically, shifts it up vertically, shifts it down vertically. Okay, that's on the outside of the function. On the inside of the function, B and C, this is all horizontal movement or movement and stretching. If B is positive, we're actually flattening it horizontally. It's the same thing as a stretch vertically, but you should think of it more as a flattening of it horizontally. And yeah, so like imagine your hand on this side of the function and on this side of the function, and you force them together and you're flattening this function out. And likewise, if we have between 0 and 1, we have a stretch horizontally. So imagine just pulling the two sides apart. That's what gives you this stretch horizontally until you stretch it so much that it becomes a flat line. Then if you get negative, well, this one's a little bit weird because the negative doesn't really show here. It's really just a flip horizontally. So we're flipping over the y-axis. But this graph is symmetric, so it's the exact same thing. However, if I were to show you, for instance, these are all good. Let me go up to here. If I were to show you, for instance, this graph, this is the absolute value. Let me change the color here real quick. Now, right, this is a flattening, or no, it's a stretching horizontally until we get to 0, which is just flat, and then now we have negative, and you see the red is now on the other side. It's a flip horizontally, and then -1, and then we start getting a flattening horizontally. So that's what B does. It's a flatten horizontally, then a stretch, and then a flip, and the same kind of behavior there. Okay, now C, this is really just a shift left and right. Shift left, shift right, all those things. And that's horizontal motion. That's the reason why I said you should think about this, whatever. You should think about this as bx minus c. These are all horizontal movements. A and D are all vertical movements. So it should be said that when you have multiple of these things here, multiple like you have a shift, a stretch vertically, and a flip, and then like all of these things together, it becomes very kind of complicated because there's certain things you have to do first when you're doing it by hand. However, you don't have to do it by hand. You can just graph these things. Like this right here is Desmos.com. I recommend using graphing software because there's really no reason to graph by hand unless you're just trying to get a picture really quick. So don't worry about doing those types of things. Just graph it with a software and you won't have to worry about which one comes first and all that kind of stuff. Okay, here I've got 3 graphs, and let me show you the parent function here. So what we're going to be doing here is saying, what do each one of these transformations do? So there's lots of transformations we can have. These are kind of simpler ones, and so they're easier to visualize what's going to happen. So in this first one, take a moment, think about it. What does this transformation does? The negative multiplying the inside of the function. So this is really saying b here is negative, because b is multiplying the x, b that is -1. And what that's doing is that's a horizontal because it's on the inside of the function. And it's negative, meaning all we're doing is flipping it horizontally. So it should just be the exact same thing as the parent function, just flipped horizontally. And that's what it is. Just flipped horizontally like that. Okay. Likewise, here the negative is on the outside of the function, and that makes a -1. Really, this is all this is doing is flipping it vertically. So it should just be the same thing as this function, just flipped vertically. And that gives us that part right there. Okay. This last one, we have a +2 on the inside of the function, which means it's going to be a shift horizontally. Which way? I told you before that if it looks negative on the inside, that's a shift right, which is kind of weird because you'd think shifting it right would be positive, because that's the positive x direction. But the inside of the function works differently. If it's positive, it goes left. If it's negative, it goes right. On the outside, if it's positive, it goes up. If it's negative, it goes down. That way works what you would expect. So this +2 is really just going to shift it horizontally 2 units, and it's going to look the exact same function. So it should be like that. Yeah.